So this is talk is on behalf of the Bias and Diversity Working Group within MIDRC, and here you have a list of all of us who are currently in the group. And I first would like to start out by pointing out that MIDRC has a lot of valuable resources out there on YouTube, not necessarily related to bias and diversity only, but I will point out those. So please, when you're find our MIDRC Media channel on YouTube, hit the subscribe button right there. And here is our last month's seminar on MIDRC bias and diversity data, tools, resources for promoting health. This was given by Ray Carlos Sa and Heather Whitney, both from the Bias and Diversity Working Group, amongst other groups within MIDRC. And this is slightly older seminar by Sanmi Coello on towards algorithms for measuring and mitigating unfairness in AI. And another seminar given by Judy Gichoya from Emory University about how AI can recognize a patient racial identity in medical imaging. So these are all available on YouTube. So please go check it out. So with this talk, I will focus on the Bias Awareness tool, which is a tool that we developed as a group within the Bias and Diversity Working Group, where we first identified 5 stages along the medical imaging AI, ML, where ML stands for machine learning pipelines, all the way from data collection and aggregation to model deployment, with the stages in between of data preparation and annotation, model development, and model evaluation. So we studied literature and gleaned from our own experience and identified biases that can arise in one or more of these steps along the way. So bias can arise in multiple steps, not just associated with one. And then we also looked into mitigation strategies, if any, and real world examples. So first, I'd like to point out that our paper on this topic will be published soon. I'm working on the proofs as we speak, pretty much. So the title is Towards Fairness in Artificial Intelligence for Medical Image Analysis, Identification and Mitigation of Potential Biases in a Roadmap from Data Collection to Model Deployment. And as you can see, the entire Bias and Diversity Working Group is a co-author on this paper. And here, this is an excerpt of a table, one of the paper where we have a bias source definition and potential mitigation strategies. And this is all based on the actual tool that is available online for anybody to peruse. And this is the QR code and the web address. So this is basically an overview of the 29 biases we identified. I know this might be a little bit small to read quickly through, but within each stage, and each stage in our AI pipeline has been color coded, where data acquisition and aggregation is blue, the data preparation is gray, and so on and so forth. So here you can see the dark colors with the white dot is the stage with which the bias is mainly associated, but then there's lighter shading in the areas, the steps that are also associated with this bias. So here you can see data collection. You have a whole very many steps this can occur or has an impact on. And also, if you say you're interested in one specific bias, or like amplification bias, or wonder what it is and where it occurs, you can see here that it's mainly associated with model evaluation, but also can occur in the data collection, model development, and model deployment. And I will go into more detail later as to what this specific bias is. I'm not going to explain all biases here. I would take a very long time, but we'll step through a few later on in the actual tool online. So here's the same as you just saw, except in the form of a Venn diagram. So a little bit prettier and more colorful, but yeah, so and emphasizing the overlap of the bias, the steps within each bias can occur, where the other graph I just showed was more like the more from A to B, straightforward to interpret. So here, the same example where data collection, you see everything in the blue box is a bias that could occur during the data collection step in your AI pipeline. And you see there are quite a few. Here, so this was the other example, amplification bias, which can occur under 4 different steps. All right, so now you ask, like, well, what if I don't remember the address of the bias and diversity tool? This is where how you would find it. This is the MIDRC homepage. You can go to the diversity menu, and then you can find it under the AI ML Bias Awareness tool, or you can go under R&D resources, and then you'll find it on that page. Okay, so when you navigate to the page, this is where you are. So this is the AI ML diversity, and you go to the AI ML awareness tool, and you scroll down a little bit. We'll try not to make everybody seasick by scrolling kind of slowly. So you'll see here's the same color coding that we used in the paper for the different steps along the AI ML pipeline, and our beautiful Venn diagram. And again, all the members who worked on this work. And here's the actual tool itself. So this is in the form of it's an interactive tree. So let's start by looking at the example of amplification bias that I pointed out earlier. So this was mainly associated with model evaluation. Then you can go here. And here we have amplification bias. So in the tool itself, you can see the little colored dots indicate which step it can be associated with the biggest circle, the main step. So, and here's the legend with the different colors indicating what what steps are involved. So here in the tool itself, we explain what it is. So in this case, amplification bias refers to the occurrences of erroneous input from machine learning that amplify already existing biases present in the training data. So it's related to training data set bias, but it's not the same. And then why it occurs, we give an explanation why it can occur. In this case, it's that your machine learning algorithm learns to predict output classes with a greater disparity than what is in the underlying ground truth, such as class imbalance in the training set or training using biased features. We also point out why it's important. Obviously, in this case, it's important because if this bias occurs, then a machine learning algorithm may skew its output based on prevalences of cases in the training data and that are not representative of those in the actual population on which the machine learning may be used. And we also give real-world examples, how it's measured. And in this case, it can be measured by measuring the evaluation on different subpopulations or by training it with data with different prevalences. And then we offer some mitigation strategies when we could find any. And in this case, it can be mitigated by using appropriately balanced training sets or by conducting influence-directed feature removal. And that's in the case you were using biased features. And the summary, and then we provide links to literature. And these are actual links if there are free open access papers available. So you would just click on the link and go there. So this was just one of the 29 biases. I just clicked on restart. So we're way at the beginning again. Now I would like to point out that some of these biases are, if you have model evaluation, you have statistical bias, right? Statistical bias is purely, it's statistical, but many of the other biases relate to equity, diversity, and fairness. So let me try to navigate back to one that has probably under data collection is a good amount of biases that have to do directly with bias and equity. So such as exclusion bias, for example. So which occurs when specific groups of user populations are excluded from training, testing, or subsequent analyses. So you can see that a lot of the biases in our bias awareness tool have to do with fairness, and then we offer mitigation strategies, which are important for anybody who's developing medical imaging AI models for generalizability and fairness for application on for the future of AI medical imaging.
Yeah, and it is great to be here. Thank you for the opportunity to talk about our metrology decision tree that I'm presenting on behalf of the TDP 3C 3D effort members. And here is a list of those members. Thank you very much, all of you who contributed. So this is my disclaimer. So the goal of this project and this decision tree is to develop information and suggestions on task-specific performance assessment metrics and analytical methods for machine learning models. So we want to identify analysis resources, including research articles, software packages, book chapters, videos when available. And we also coordinate with all the other projects, but especially with our sister project, Technology Development Project 3D, on how to use sequestered data to provide reference analysis and performance benchmarks. So I just wanted to briefly mention some of our motivation for doing this. And I'd like to start by mentioning that not all metrics are appropriate to evaluate performance for a given task. For example, overall accuracy is a metric that's commonly used. It's defined as the number of correctly classified cases over the total number of cases in a classification task. And it might be a good metric in some applications, but in others, it might be a terrible metric. So consider a classification task where the prevalence of a particular class overwhelms the others. As it frequently happens in medical imaging, we typically have a lot more negative cases than positive cases. So in this situation, a model that quote unquote predicts all cases are in the prevalent class, even without looking at the image, will have a high overall accuracy, but it will be useless. And we see this actually in fields other than medical imaging. For example, in Earth resource remote sensing, a relatively recent paper mentioned this as an important factor. The title is "Overselling Overall Map Accuracy Misinforms About Research Reliability." And they looked at a lot of publications in different areas in top journals, and they found that maybe close to 90% of all publications that they looked at use overall accuracy as their main metric, which, as I mentioned in the previous slide, may not be a good metric in many tasks. Another example for our motivation is that sometimes performance metric reports can be inadequate or inappropriate. So this paper, not very recent, but I think still relevant, says in a tongue-in-cheek manner that sensitivity and specificity and their confidence intervals cannot exceed 100%, and gives an example of a paper that produced 95% confidence intervals exceeding 100%, as you see at the bottom of the first paragraph. So we'd like to avoid situations like this. So our goal in developing this decision tree is to help MIDRC users in selecting metrics and reporting performance. So we ask users a series of questions to guide them through a decision tree for metric selection. And the final leaf, we have metrics and suggested resources. And we hope that this will help researchers from different fields who employ MIDRC data select task-based performance metrics, encourage use of consistent metrics for similar tasks, which will help the comparison of results from different studies, and help stakeholders put reports from MIDRC data into proper perspective. So this is the web address for our decision tree. It's live. And when you click on this link, or you can go to it by first going to midrc.org and then following links through TDP3C, when you arrive at this page, the first thing you will see is a page like this, where we describe 5 general tasks that we tackled in decision tree that are relevant to COVID-19. And these tasks are classification, detection or localization, segmentation, time to event analysis, and estimation. So we also try to guide the user by providing hover text. So for example, when you hover over this classification, it'll tell you what a classification problem is. For example, classification of cases as COVID-19 positive versus COVID-19 negative, etc. So I'm going to try to take you through some branches to see what kind of information we provide, and I'll do this through the classification branch. So when you click on classification, the first question that you see will be this: what best describes your clinical classification task? Is it a binary classification, or is it a multi-class classification? And again, we have some information about what we mean by binary and multi-class classification in our hover text. So let's say you click, just one second. Let me quickly talk about first a simplified flow chart of our decision tree. This is a simplified flow chart of binary classification, where you see the questions that we ask and the type of metrics that we will provide. And this is a simplified version of our flowchart for multi-class classification. Again, the questions and the type of analysis. But when you go into the tree, it's actually a lot more detailed than this. And I will take you through this classification task to show you a little bit more detail. So again, going back to the previous page, let's say you go into the classification branch and then choose the binary classification task. Once you do that, the next question that we're going to ask is, does your reference standard or truth have negligible unreliability and variability? And these questions, I will put them in orange boxes. So this is the question, and this is how it looks on the website. Sorry, just one second. This is how it looks on the website. Let's say that the answer to this question is the first option: negligible unreliability and variability. So your answers, I'm gonna put them in, oh, sorry, something happened. Yeah, your answers, I'm gonna put them in green boxes. So let's say you choose negligible unreliability and variability. So the next question that we ask is, what type of output, what is the type of output of your AI ML algorithm? And let's say that the answer to this is the second option, non-binary. So when you select non-binary, then the problem is two-class classification based on a reference standard with negligible variability and non-binary AI/ML output. And then we go to these recommended evaluation approaches, where we list 3 types of approaches: receiver operating characteristic analysis, precision recall analysis, and predictive operating characteristic, or PROC curve analysis. So let's go a little bit more into these. So let's say that you choose receiver operating characteristic analysis as your preferred, as a metric that you would use. Then we have this page where we describe what receiver operating characteristic analysis is. We even have a video by my colleague Brandon Gallus on ROC. And then within ROC, we provide a number of different metrics. So the metric that you derive from an ROC curve can be the area under the ROC curve, can be partial area, or can be a selection of a single sensitivity specificity operating point. Again, we provide examples, and also we provide links to websites that implement ROC analysis and provide the area under the ROC curve with the error bars, such as this IMRMC package that's at the FDA website in our regulatory science tools, or the METS ROC software from the University of Chicago, or the ORDBM package from the University of Iowa. So this was just receiver operating characteristic. If you choose precision recall analysis, again, we have an explanation about what precision and recall are, and then we again provide links to papers and available software for performing precision recall analysis curves and for finding the area with the error bars. So this one is an example of binary classification. For multi-class classification, again, I won't go through all the different steps, but assume that you choose this path where you're looking at multi-class classification based on a reference standard, negligible variability, and a single label output. We again have these recommended analysis methods for this situation, where we list a bunch of them, such as balanced accuracy or F1 score or others. And then again, we provide links to software and we provide practical examples. So this was just for the classification branch. We similarly have a simplified flowchart for detection localization, where we ask the user about the endpoint of their task, their reference standard, the variability and reliability of the reference standard, and what kind of output your model gives. And based on that, again, we have these approaches such as operating points or operating curve analysis, where there are additional details. Likewise, for segmentation, we have a number of questions and then related metrics. Time to event analysis. Again, we ask about the endpoint of your task, if both event and time are available, and some underlying assumptions. And then we provide a number of metrics depending on your choices, and likewise for estimation. So in summary, our technology development project is working on a decision tree tool for metric selection and reporting for machine learning models applied to MIDRC data. And a draft has already been released on midrc.org. So I encourage everyone to go there, to play with the tree, to put, whatever scenario you're thinking about as answers to your questions, and see what kind of metrics we recommend. And please help our tree grow with your feedback. Thank you.